Hello, dear students. Let's see this question 3.17 of Irodov from electrodynamics. The question states, suppose the surface charge density over a sphere of radius r depends on a polar angle theta as sigma is equal to sigma naught cos theta, where sigma naught is a positive constant. Show that such a charge distribution can be represented as a result of a small relative shift of two uniformly charged balls if radius r whose charges are equal in magnitude and opposite in sign. Restoring to this representation, find the electric field strength inside the given sphere. So in this question, there are two parts. First part says that the given charge distribution can be resultant of the superposition of the two uniformly oppositely charged spheres with a little shift, and then find the electric field. So we'll proceed in the reverse order. First, we'll find the electric field due to the given charge distribution. And then I'll show that this electric field is same as that of the two non-conducting uniformly charged identical spheres having a opposite volume charge density, and a little shift is made between them. So if I'm going to do the first part, that is to find the electric field of a sphere of radius r whose polar angle theta is equal to sigma naught cos theta. It is same as the question number 3.16. So let's revisit the question number 3.16, which I had solved. So the question number 3.16 says that sphere of radius r carries a surface charge density sigma is equal to vector a dot r, where a is a constant vector, r is the radius vector of a point of the sphere relative to its center. Find the electric field center strength at the center of the sphere. So this is a sphere, radius r, and this is a constant vector a, and at angular position theta, the position vector is r vector. Its charge density given a dot r, angle between vector a and r is theta, so this sigma is equal to ar cos theta. And we have solved this. You can see the video, or you can use the result of the answer to question number 3.16. And if you look this charge distribution, this varies as a is a constant, r is a constant, varies as cos theta. So cos theta is maximum at theta is equal to 0. As we go like this, here on this part charge density is positive, and on this part charge density is negative, and it varies something like this. Maximum charge density is here charge density is 0, here maximum negative, and it decreases as we go to the, we can say, kind of at pole. And its electric field will be opposite to a vector, and we have already solved that electric field is equal to minus a vector r 3 epsilon divided by 3 epsilon. In terms of magnitude, I can simply say that this magnitude is AR 3 epsilon naught and opposite to a vector like this. Now looking to the charge distribution given the question number 3.17. Same sphere, and let me assume that in the direction of a vector there is a direction z axis, and with respect to z axis at angular position theta there is a position vector r. And at this point, surface charge density is sigma is equal to, this is actually sigma naught. Sigma is equal to sigma naught cos theta. And if I compare this charge density with this charge density, I can say that AR is equal to sigma naught. And the charge density would be same like that because it is varying with cos theta. So I can write AR is equal to sigma naught. So everything is the same. Except AR, there is a sigma naught. So this electric field would be opposite to z-axis, and in place of AR, I have to just put sigma naught. And because it is opposite to z-axis, I will write E vector is equal to sigma naught by 3 epsilon naught minus k cap. That is the answer to this electric field inside the given sphere. And you can see that this electric field is uniform everywhere. Everywhere it is opposite to z-axis. So everywhere electric field is like this, not only at this point, but at any point inside the sphere, electric field is uniform. And now let's look another situation. In this situation, we have two identical spheres of same radius and charge density minus rho and plus rho. If I overlap them, the electric field will be everywhere zero because there will be the charges will cancel. So what I'm going to do, I am just bringing them closer a little bit so that some part of them overlaps and some part of them does not overlap. So like this. So the overlapping part, the charges will cancel. So this part has a, uniform charge density minus rho and this part has a uniform charge density plus rho. And I want to find the electric field in the overlapping region at any general point, say P. Because of this part, minus rho, electric field here would be towards O, and because of plus rho, electric field will be towards away. So electric field because of the minus rho square would be say E minus, and electric field because of the plus rho is say E plus. And the net electric field is the vector sum of these two electric fields like this. E net is equal to E minus plus E plus. And I'm going to use a result that inside a uniformly charged solid non-conducting sphere, electric field at a point is equal to rho divided by 3 epsilon naught r vector, where r vector has a tail at the center and head at that point at which electric field is sought out. So this E minus would be minus rho by 3 epsilon naught O P vector, and E plus would be plus rho by 3 epsilon O dash by O dash P vector. So I can write like that. And if I simplify this, I can take minus 3 minus rho by 3 epsilon naught. I'll get OP minus O dash P, and OP minus O dash P would be nothing but O dash P. So what you can see that the electric field inside this overlapping region is opposite to O dash vector. And O dash is a constant vector because O is the center of this sphere and O dash is the center of this sphere. So in the overlapping region, electric field is uniform, equal to minus rho by 3 epsilon naught O dash vector and opposite to O dash vector. So what happens if I shift this minus rho sphere here and this here? I mean, I want to keep on increasing the overlapping region. So that becomes like that. So in that case, if I keep on increasing the overlapping region, the shift of the centers, or you can see another way, just overlap them 100%. Just overlap them 100%, then slightly shift one with respect to other. So overlapping region is a very large region, so there is no charge here. And here there will be positive charge, here there will be negative charge. So this positive negative charge can be treated as a little charge at the surface. At this point, the charge is 0. Here the charge is maximum, here is charge is minimum in negative sign. So this charge distribution is something to this charge distribution, and the result will say. So this result, as I've written here, electric field within this sphere would be E is equal to minus rho by 3 epsilon O dash vector. And if I compare to the electric field in this situation, the electric field in this situation was sigma by 3 epsilon naught minus K vector, or I can write minus sigma by 3 epsilon naught K vector. So I can think that this situation in which there is a surface charge density sigma is equal to sigma naught cos theta is equivalent to a small relative shift of two uniformly charged balls if radius r of radius r whose charges are equal in magnitude and opposite in sign. And what will be the correspondence between this sigma naught and this rho, and the corresponding would be given by this equation, and that correspondence would be rho O dash is equal to sigma naught. So we have shown that we have first of all found the electric field because this charge distribution, and actually this charge distribution is nothing but the superposition of two identical spheres having charge density rho and minus rho, and a very small relative shift between them is made such that the overlapping region is chargeless, and non-overlapping region has the same charge surface charge density as that of this sigma is equal to sigma naught cos theta. So thank you for watching.